Now let us see what is gas stoichiometry. This is nothing new. This is exactly what we did in stoichiometry chapter to calculate the mass relationship between reactants and products in a chemical reaction. So first we will have a balanced chemical equation and the coefficient represent the number of moles. So in this equation you can see 1 mole of nitrogen combines with 3 moles of hydrogen gives you 2 moles of ammonia. That means the coefficient represents the number of moles. So here in gases, according to Avogadro's number, our Avogadro's law, we know the number of moles is directly proportional to the volume. So for gases, reactants and products, we can take the coefficient as volume of gases. If the pressure, volume, and temperature of an ideal gas are known, stoichiometric calculations can be performed. So that's what we are going to do in gas stoichiometry section. So we can calculate the volume if we know the coefficient, as I said. So 1 mole of nitrogen means 22.4 liter. So that means 1 mole of any gas will have a volume of 22.4 liter. So 3 moles will have 3 times. This is at STP, standard temperature and pressure. So 3 moles means 3 times 22.4 and 2 moles mean 2 times 22.4. Where is that 22.4 coming from? Let me show you. This is from our ideal gas law, PV equal nRT. So for 1 mole, that N equal 1 and R is 0.08206 and temperature 273.2, which is the standard temperature, and the standard pressure is 1 atm. So at STP, 1 mole of any gas, irrespective of the gas, will have a volume of 22.42 liter to be accurate, but we will just round that one to 22.4 liters. That's how that 22.4 is coming from. Okay. So the units are cancelling. So therefore the molar volume is 22.4 liter at STP, standard temperature and pressure. So normally there are 2 types of gas stoichiometric problems, one with a standard temperature and pressure and 2 non-standard temperature and pressure. That means at a room temperature and pressure. In both cases, the steps are 1. Write balanced chemical equation for the reaction. Okay. Second step, find moles, that is convert if it is grams, gram mole conversion. If it can be from molarity and using ideal gas law. So there are different ways you can calculate the moles. If grams is given, gram to mole conversion. If molarity is given, molarity equal number of moles over volume in liters. And we'll go over it again. And the ideal gas law also can be used for finding the number of moles. And then do a stoichiometric conversion between the chemicals. As we have just discussed, compare the moles, that is by coefficient. And answer the question, depends on what they are asking for. Okay, so 22.4 liter per mole for STP gases, and for other gases we will use PV equal nRT for non-STP gases if it is not at standard temperature and pressure. All right, let's see. So breakdown on glucose is below. Calculate the volume of carbon dioxide. It should be off, sorry. The breakdown of glucose is below. Calculate the volume of carbon dioxide produced at 37 degrees Celsius and 0.5 atmospheric pressure when 5.6 grams of glucose is used to completion in this reaction. So the equation is given like this. And what are the things given? I will write under the given. So glucose, calculate the volume of carbon dioxide. So I will put a question mark under carbon dioxide, which is the unknown, which is volume of carbon dioxide. Okay, and the given mass of glucose is 5.6 gram. Temperature is in degrees Celsius. We have to convert that one into Kelvin, and the pressure is 0.5 atm. So moles equal mass over molar mass. So 5.6 is given. So that's the first step. We converted that one into moles. And then this is the way I got 180. That's the molar mass of glucose to calculate the number of moles. And then 1 mole of glucose we can see from the balanced equation that corresponds to 6 moles of carbon dioxide. Therefore, 0.03 moles equal how many moles of carbon dioxide? So 6 times 0.03 will give you 0.18 moles of carbon dioxide. This is the dimensional method if you would like to do that way, okay? But in both cases, the answer will be same. And now we have to calculate the volume. We have 0.18 moles. So how we will calculate the volume? So PV equal nRT. So this is not under standard condition because the temperature is different, pressure is different. If it is standard condition, it should be 0 degrees Celsius and 1 atmospheric pressure. Since it is not under standard condition, we have to use PV equal nRT formula. So pressure is given as 0.5. Volume, what's the volume? That's what they are asking us to calculate. And number of moles, we already calculated 0.18. And the R value is 0.082. And we have to convert that temperature into Kelvin. And now we can calculate solve for V. So you can see that it is 9.15. So this is not under standard condition. One example from non-standard condition, correct? All right. So now, following decomposition reaction takes place when the airbag inflates in a vehicle. If an airbag has a volume of 60 liters and is to be filled with nitrogen gas at 1.5 atm at 26 degrees Celsius, again, this is not under standard condition. They are asking how many grams of NaN3 must be decomposed. Okay. So this is another type of question under gas stoichiometry following decomposition reaction. So that when the airbag inflates. So this is another gas law application you can see. So let's see how to do this one. Given the data for nitrogen, they gave all the data for nitrogen and they're asking for unknown mass from the reactant side. So what we will do first, we will find number of moles, correct? How we will do that? PV equal nRT. I am substituting everything, converting the degree Celsius to Kelvin, and we have pressure given, we have volume given, and we know the R value, and now we know the temperature in Kelvin as well. So first we calculated the number of moles because we already have the balanced equation. So second step, number of moles calculation. And then what we will do next is do a stoichiometric conversion. So what is the relation for 3 nitrogen to NaN3? Therefore, for 3.67 moles, how many? So we can do that one by using dimensional analysis if you would like to do that. So for 2 moles of NaN3, we have 3 moles of nitrogen. And we got by calculation 3.67 moles of nitrogen from the given data. And we know for each 1 mole of NaN3, we have 65 grams of NaN3. When you calculate the molar mass, you will get that. Sodium is 23, nitrogen is 14 times 3, correct? So that will be 42. 42 plus 23 is 65. So, and now multiply in the numerator and divide with the denominator number. So that will be 159 grams of NaN3 will be required. Alright, so you can try this one by yourself. Again, you can see this is not under standard condition by looking at the temperature and pressure. Okay, so try yourself, and if you have any question, let me know.